So the first speaker is Professor Mehetov from CNRS, and he is going to talk about normal approximation, the Gaussian multiplicative chaos, and XS1 for the sine process. So please.
Thank you very much for this invitation. It's a great pleasure to be with you, even though virtually. So let me just start with the sine process. So with the sine kernel. So, and to almost every realization of sine kernel, I can assign a random
recording in progress.
Random entire function. So in fact, it is convenient for me to write it in two variables, t and s. So product t minus x, s minus x. X are particles in x, my configuration. This is my configuration. And t and s are complex numbers. It is convenient to think of them as complex numbers, let's say in the upper half plane, for example. So my function, most important for me will be the case when s is taken to be, for example, 0, and then I obtain an entire function of t. So gx t0, entire function of t. Okay, so I'm interested in the behavior of this function, and let me formulate the first main result of the talk. I will formulate it in the form that is most convenient for me, but so just for the purposes of this talk, is the following: that gx of r plus rt plus ri squared dt. So this is a measure on 0, 1. This random measure, the randomness is in x, converges to Gaussian multiplicative chaos. This is Gaussian multiplicative chaos corresponding to the standard. It's one-dimensional, corresponding to the standard kernel, a little bit corrected with logarithm of t minus s. And the parameter is the critical parameter of getting out of the L2 regime. So here we are not in L2 regime, but barely not. So this is the first main result. And so the corollary of this result is in fact that the sine process has XS1. What do I mean by this? I will right now explain. The sine process has XS1. That is to say that there exists a function. So let us recall that this is projection onto Pelley-Wiener space. S is projection onto Pelley-Wiener space. Onto the Pelley-Wiener space. So of functions, let us recall Pelley-Wiener space of functions in L2 whose support of the Fourier transform is in minus pi. Okay. And so the claim is that for almost every configuration with respect to the sine process, almost every x, and any particle p in x, pq, distinct particles in x, so there exists a non-zero function in Pelley-Wiener space such that f in restriction to x minus pq is equal to 0, so f not 0. At the same time, there does not exist, so if f in restriction to x without p is equal to 0, then f itself is equal to 0. So this is the result. This is point A and this is point B. Okay. So these are the two main results. This is a corollary of this. And the key point in obtaining these results, so the convergence to the Gaussian multiplicative chaos for the random entire function, which is the scaling limit of characteristic polynomial of random matrix. So this is just if a sine process is scaling limit of, let's say, circular unitary ensemble, then this is just, in fact, scaling limit of ratio of two values of characteristic polynomial of my random matrix. Let's say random unitary matrix or random Hermitian matrix, the matrix that you prefer. And so this quantity converges to random measure, the Gaussian multiplicative chaos, and this corollary follows. This, of course, continues the line of investigation started by Fedorov and Jan Fedorov and Keating and many other authors. Many investigations were undertaken for this such convergence for finite number of particles. But here convergence as number of particles grows. But here please observe that convergence takes place as r goes to infinity and the number of particles is infinite from the very beginning. It's infinite from the very beginning. Okay, so the key step is the following theorem about normal approximation. Is the following theorem about normal approximation for additive statistics of the sine process So what is it? This normal approximation for additive statistics of the sine process just is the following statement. So we consider as usual SF to be the sum of an observable along my sine process, so along the particles of a realization. X here is configuration, I'm summing over its particles, and just let us recall the central limit theorem of Soshnikov, which in fact I should say builds on earlier work of Johansson for example, circular unitary ensemble. This is the following statement, that for f in Sobolev space h1/2, so space of 1/2 Sobolev regularity, usual Sobolev Hilbert space h1/2, so for f in h1/2, the additive statistics SF rescaled by R converges in law to the normal distribution as R goes to infinity. Please observe that there is no additional normalization, converges to normal distribution. Let us assume that f is of average 0, of integral 0, so just 0, and here I have Sobolev semi-norm over 4 pi square. What do I mean by Sobolev semi-norm? Just Sobolev semi-norm is the integral lambda f lambda squared d lambda, or what comes down to the same, this double integral over x and y, dx dy. Okay. So just this is the Soshnikov central limit theorem. And so what I need and what I establish is a rather stronger fold of the Soshnikov central limit theorem. So stronger in what sense? So clearly in convergence to Gaussian multiplicative chaos and such similar convergences for exponentials. So in fact, already one can see the logic between the results that I just formulated. So in fact, the additive statistics, for example, the logarithm of characteristic polynomial exhibits normal behavior, and I'm interested in its exponential, so in exponential of an asymptotically normal variable. And it is well known that even for Gaussian processes, the convergence to Gaussian multiplicative chaos is obtained by considering the range of values of my random normal variable on the order of magnitude of variance rather than the square root of variance. So, in fact, I need to compare my random variable to the Gaussian random variable, but not just all the way up to values on the order of magnitude of variance. But in fact, this is precisely what is possible, and this is the normal approximation result that I formulate, normal approximation. So we fix, it is possible to formulate it in a little bit more general terms, but let me formulate maybe less general result, but sufficient for our purposes. So we take the distribution, we take a function which is in h1 half. In fact, we also need it to be in h1. So we need stronger assumption. We take function in h1. We only take functions in L infinity. This is just always our assumption. So we take the distribution. Let me denote MF, the distribution, the law of SF. So then the claim is that the integral of some function g some smooth test function, g u t dmf over the same thing over normal distribution, dn sigma f. So this is sigma f square, this is my semi-norm, sigma f, yes, the normal distribution of this, let me write sigma f square. So this quantity, again, if I wanted t only to be some bounded quantity, this assumption would have been enough. I want, however, t to go all the way to the variance. So I need one additional assumption, that f holomorphic in a strip, Okay. So then this quantity minus some special function, some specific function c, depending on f, c of t over sigma f square, this quantity is less than some constant over sigma f. So again, what is this estimate uniform in? This estimate is uniform. We assume that the L2 norm, L2, H1, not L2, H1 norm of f is bounded by some constant. We assume that f is holomorphic in a strip, in that H1 norm is bounded also in a strip. So let me write it like this. Also in the strip. In my strip. The strip is fixed. That is to say, H1 norm of f plus I delta. These H1 norms, I need to be bounded. These are the ones that matter in this problem. And t is taken. What is the value for t? T is taken between some constants over sigma f square. So this is the value for t. T is just some constant O. So please observe that even though H1 norm is bounded, clearly H1 half norm can explode. And in fact, this is exactly the situation that will arise in my study of characteristic polynomials, as we shall see in a moment. But my point is again that g is just, let's say, C infinity of compact support. It doesn't matter, just continuous function of compact support. It doesn't matter. So just please observe that. Let's say C1 compact support. However, because I smooth a little bit. So I smooth a little bit. Okay. So I have my function. I have g is fixed. So the implied constant depends on g. I have my value, probability, how do I say, probability distribution at the range comparable to the variance. I compare it to the normal distribution. Then there is a constant. This is just a fixed function. Then there is a constant which compares between them. This function is close to 1 in the neighborhood of 0. CF of 0 is equal to 1, in fact. So in the neighborhood of 0, this is close to 1. So this function is completely dominated by H1 norm, which in our considerations will remain bounded. And this is precisely the estimate that this is comparable to Gaussian distribution with this range of error. The constant k depends on all implied constants, namely on this k. Let me put k in there. On this k and on this constant, on the H1 norm of all of my functions, and this is the result. And this is the result on normal approximation. This is the result of normal approximation. Okay, are there maybe any questions? Because now I switch to the other blackboard and I apply it to the characteristic polynomial. So any questions about the normal approximation, or I can continue? Okay, so let me continue with the characteristic polynomial. So now I apply all the above considerations to the function, to the logarithm of my random entire function. So I consider the function. S, well, I put here t and s, let me put z and w. S z w of x, which is the additive statistics corresponding to the log z minus x minus log w minus x. Z and w are in the upper half plane, so log is defined in principal value. There is absolutely no question with defining the log. And in fact, the main point for me will be the real part of this quantity anyway. So my main point will be the real part of this quantity. But in fact, I can have also the real and the imaginary part. Now, it is useful to recall the Stochastic limit theorem and to consider Gaussian field, of which, so I consider, let me erase the definition of the entire function. We remember that we're interested in the exponential of this quantity. Okay, so now I consider Gaussian field. What Gaussian field? So what Gaussian field? Gaussian field YZW. So this will be, so Gaussian field. Maybe let me write Gaussian process even. It's process, so it's a Gaussian variable, but a Gaussian process. So it is indexed by 2 points in the upper half plane. It satisfies, as one can see by looking here, the cocycle equation. YZW is equal to YZU plus YUW. So UZW in the upper half plane. So in the upper half plane. Okay, so just the variance of my Gaussian random variable will be the Sobolev 1/2 semi-norm of this quantity, and it can be computed quite explicitly. So the variance YZW is equal to the log 1 plus the square over 4 imaginary part. So now comes the key point. This quantity is invariant under Lobachevskian isometries. So the upper half plane is the Poincaré model for the Lobachevsky plane, and in fact, the Lobachevskian isometries preserve the Sobolev 1/2 norm. This should not surprise us very much. In fact, if one looks here, one recalls that where does Sobolev 1/2 norm emerge? Sobolev 1/2 norm emerges when we do a scaling transformation. When we take this function, when we take our function, let us recall, SF rescaled by R. This converges to the normal with the Sobolev 1/2 semi-norm. So, but please observe that just clearly, since I have this over R, well, it is clear already that shifting ZW by one constant doesn't change this function, so there is no surprise. Since the Sobolev 1/2 semi-norm emerges from this scaling, then it is clear that multiplying ZW by the same real lambda doesn't change the Sobolev 1/2 semi-norm. It is also clear, it can also of course be verified directly, but just it is also clear from the form of the Stochastic limit theorem. And a separate verification that is also true is that the Sobolev 1/2 semi-norm does not change by inversion, doesn't change if I replace z by -1 over z. This is separate verification, it can be done. So this asymptotic field, or so to speak, obtained from the Stochastic limit theorem. So the Stochastic limit theorem says that this quantity, this additive statistic under scaling converges to Gaussian, converges in law to Gaussian random variable. Let's consider corresponding Gaussian process indexed by pairs of points z and w. This Gaussian process is invariant under Lobachevskian isometries. Why zw? Invariant under Lobachevskian isometries. Invariant under Lobachevskian isometries. So the law is in the law of the process. Zw. Invariant under Lobachevskian isometries. So this is a key point. So let us now draw this this random variable. Please observe, by the way, in terms of Lobachevskian distance, this variance can be written in a very simple form. So it's just logarithm of 1 plus cosine hyperbolic of Lobachevskian distance over 2. Over 2. 1 plus cosine hyperbolic of Lobachevskian distance over 2. Yes. So please observe that. Please observe that, by the way, for large values of the distance, the variance is essentially the distance itself. The variance is essentially the distance itself up to additive constant. But at the same time, well, it is different. So it is similar to Lévy field on Lobachevsky plane, but not quite, not precisely Lévy field. It's a little bit different. Okay, so okay. So we consider this Gaussian process. Let us look at this Gaussian process more attentively. So just the let us look at it in the circle model of the Lobachevsky plane. So I take some reference point and I take some curve. It can be circle or it can be horizontal. For me, it's more convenient to take horizontal. And the horizontal converges to the absolute. And this is me. This is the observer. So I'm here. I'm the observer, and the horizontal converges to the absolute, and I'm observing the horizontal converge. So since the triangles are thin in Lobachevsky plane, so this variance is essentially the distance up to additive constant. If it is large, the variance is essentially the distance. So the correlation between the correlation between covariance between y, let's say O is the observer, OZ and OW, Z and W converge, O is the observer who stays fixed, and Z and W converge to the absolute. This is essentially the Gromov product. Again, the notation means up to additive constant. Additive constant which does not depend on anything, it's not like 3. So this is essentially the Gromov product. Essentially the Gromov product. In particular, it stays bounded. The Gromov product, it stays bounded. The Gromov product is, it is all very geometrical here. The Gromov product is the distance from the observer to the inscribed circle in my triangle. But this distance, as the triangle goes to the absolute, it converges, this distance converges to the distance to the inscribed circle of the triangle, of which 2 vertices are on the absolute. And this is finite distance. So the correlation between my Gaussian random variables, even though their variance goes to infinity, the correlation converges to a limit. Converges to a limit. It can be explicitly computed. It is our favorite logarithmic kernel just from the very first work of Jean-Pierre Cahn on the Gaussian multiplicative chaos. So, perfect, just for this Gaussian process, in the limit, as I converge to the absolute, I obtain a Gaussian limiting field, and this Gaussian limiting field admits an exponential. So please just one can take one's favorite proof of convergence to Gaussian multiplicative chaos, and it works. So just for me, the most convenient formalism is the formalism of Berestitsky, which relies on the theorem of Gersanov. Also in the Gaussian case, just the original proof of Jean-Pierre Cahn, it works. So just your favorite proof of convergence to Gaussian multiplicative chaos, it works. In the Gaussian case. Please observe, however, that my situation is not Gaussian. It is not Gaussian. It is not Gaussian. And in the remaining 3 minutes, let me just very briefly explain. So how I proceed. So I proceed to prove the normal approximation theorem. So this is precisely the normal approximation theorem, which allows me to compare the distribution of my additive statistics to the Gaussian statistics, to the Gaussian law. So this is precisely the approximation that allows me to obtain convergence to Gaussian multiplicative chaos, not for limiting measure, but for the additive statistics itself, which is what I want. So let me just say very, very briefly that the proof of the normal approximation theorem, it relies on 2 ingredients. First ingredient is the scaling limit of Borodino-Kunkov-Geronimo case formula. It looks quite precisely the same. Geronimo case. It looks quite precisely the same. So multiplicative functional under the sine process, which is the analog of the top, is determinant of psi exponential of f. Let me write it like this: of exponential of SF, exponential of analytic statistics. As usual, f is represented as the sum f plus plus f minus. F plus has Fourier transform in positive part, f minus has it in negative part. So it is equal to the first Sigur term, the exponential of f. The second Sigur term, here there arises this pi square factor. So let me write it in this form: f plus f minus tilde. Tilde means the inverting, the Fourier transform of h1 half in h1 half. Then I have the very important term, which is precisely the Borodino-Kunkov-Geronimo case term, which is the determinant of a Hankel matrix. So just here it is. there are continual Hankel operators. Where the function h plus minus is the exponential of f plus minus f minus, and I need to change by 2 pi. 1 over 2 pi minus f minus 1 over 2 pi minus f minus over 2 pi, and I need to rescale by 2 pi, and h minus plus is the same thing with plus interchange by minus. So this is the scaling limit of the Borodino-Grigorov-Geronimo case, and the key ingredient in the proof of the normal approximation theorem is also an estimate for higher frequencies, which says that this very exponential, let me write it in this term, exponential under the sine process lambda sf is less than exponential minus delta h1/2 norm delta absolute value of lambda, provided lambda itself is less than some constant times this h1/2 norm. And this key estimate is obtained by using the change of variable formula of Johansson, the analog of change of variable formula of Johansson, so replacing the fast oscillating integral, replacing by exponentially decaying integral, and and in the so moving the contour of integration in the proof of this estimate, the key role is played by quasi-symmetries of the sine process, by the fact that the sine process is quasi-invariant under diffeomorphisms of compact support. This is precisely what allows to move the contour, which in turn implies this estimate. Together with this estimate, let me just very briefly say that CF is precisely the correction term of Borodino-Geronimo case. This is precisely what it is, CF. So this is what gives rise to the correction term. One obtains the normal approximation estimate, and from the normal approximation estimate one obtains the convergence to Gaussian multiplicative chaos, as I had written before, and the axis 1 for the sine process. Let me just reproduce these results, and thank you very much for your attention.
Thank you very much for the nice talk.
So let me just write this.
Oh,
Thank you very much. No, I'm ready to take questions. I just write the result, just reproduce the result here. This converges to GMC, and just the sine process has axis. So to have all results on the same blackboard. Yes, thank you very much.
So, are there any questions?
Hello, Sandra.
Yes, I'm saying yes, please.
So in your first result, how about you write r plus rt? If we write r plus 2rt, this kind of thing.
Yes, it's the same. Yes, of course.
It's the same.
It's the same. Yes. I just write it in this form, so I could write it even for t from 0 to infinity, but with convergence on compact subsets. Yes, it's the same.
So this does not change the GMC, the exponential parameter.
Please say again.
So when you change this r to certain 2r, this the first r is like different, like for instance 2r, and the second is r, and this does.
So please observe that here also I have r. So this corresponds precisely to the picture just that I wrote on the other blackboard. Let's go to the other blackboard for the moment. So just this is point 0, but it will be in upper half plane. It will be point I. So horizontal will become horizontal line. This is horizontal line which converges to the absolute. which converges to the absolute. So I take some arc of horizontal and it converges to an arc on the absolute. So here the height is I over R. And then I apply Stochastic. I apply Stochastic, I expand everything by R. And here, like this, I obtain, so looking at this picture, so again, the observer is in fixed position. These points go to the absolute, so in upper half-plane model, 0 goes to I, let's say. It could be 2I, 10I, it doesn't matter. So just this arc goes to the absolute, and then by applying Stochastic scaling RT, we obtain the final result. I hope I answered your question, Nancy.
Yes, but another question. This to the square, how about to square by 4 or 6?
Yes, this is a very good question. So, up to some power, so this is a very good question. I think, so when you prove something, you become optimistic that you can prove more. So I think it is also possible to push this result into supercritical regime, I think, because this result, the normal approximation, so I erased it, but let me write it again. So the values of t were just less than some constant times variance. This is what the formula I have here. So just, this can be any, so I believe that this can be also put to supercritical regime. Let us recall that in supercritical regime, the behavior is quite different, so there is conjecturally some Poisson process that lives on maxima of my random entire function, so it's different behavior, it's not Gaussian multiplicative case anymore, it's not, the limiting measure is not just countermeasure as in this situation, but the limiting measure is point process itself. The limiting measure lives on maxima of my random entire function. This is conjectural, but I think there is this normal approximation theorem gives hopes towards the truth of this conjecture, also in supercritical regime. But I don't have proof right now to tell you.
Okay. Thank you very much, Sasha. Nice talk.
Thank you very much.
Yeah, we are.
Thank you very much. Thank you very much. Yes.
Yeah.